The Lagrange theorem will allow us to calculate the extrema of a function restricted to some other region. For instance, if the function is a function whose domain is in R3, and we have another function that determines a surface where we want to restrict this function to. So if in those conditions, if the function has local minimum or maximum at a point, then what's going to happen is that the gradient is actually a multiple of the gradient of the constraint function. And this multiple here, so for instance, is equal to 3 times the gradient or to 4 times the gradient. So this number here, the multiple, is going to be called the Lagrange multiplier. So the function can be in R3, it can be in R2, so the condition is the same. So the gradient, of course, is going to have more or less components if the function is in 2 or 3 dimensions. So the theorem allows us to construct a method in order to calculate the extrema. So if we know that the gradient is going to be a multiple of the other gradient, so we can find the candidates to be extrema by finding the points that satisfy that condition. So the condition of the gradient, if it's with 3 components, will be that the derivative respect to x is a multiple of the derivative respect to x, the derivative respect to y is a multiple, and z is also a multiple. So the 3 first equations is just the writing down of what means that the gradient is a multiple of the other gradient. And then we add the condition that the constraints, let's say, that g evaluated at the point is equal to 0. Well, the solution of this system of equations is going to give us a list of points that are going to be a list of candidates to be extrema. So what do we do with that list? Well, we evaluate the function f, the original function, at these points, and then we compare all of these values. The biggest one will be the maximum, and the smallest one will be the minimum, and we will have at what points those minimum and maximum values happen. So, for instance, let's start with this example that will be in 2 variables. This is a function of 2 variables. Instead of a surface, it's going to be a curve, right? Since we are talking now in something like this, in something that is 2-dimensional. First of all, we write the function. The function g of xy is going to be equal to 4x squared plus y squared minus 8, right? We put everything in one side, and then we have now the 2 functions, the function f and the function g. And so now we start by writing down the conditions on the gradients. So we need to calculate the partial derivatives of f and the partial derivatives of g. So the partial derivative of f respect to x, the function x is xy, derivative respect to x is going to be just y. And the derivative respect to y is going to be just x. We do the same with the function g. The derivative of g respect to x is going to be here 8x. And the derivative respect to y is going to be just 2y. And so once that we have this derivative, we write down the system of equations that we saw before, given by the theorem. So I remind you that the system of equations is going to be given by the gradient of f equals to a multiple of the gradient of g and the condition g equals 0. So this is going to be our system of equations. So in our case, it's going to be y is equal to a multiple of 8x, and x is going to be a multiple of 2y. So these are the equations given by the gradient equal to a multiple of the other gradient. And then the last one will be g equals 0. G is this, so the last equation will be 4x squared plus y squared minus 8 equals 0. So this is the system of equations that we have to solve to find the candidate points. So let's start. Let's write down this one's beta. That will be y equal 8 lambda x. From this one will be x equal 2 lambda y. We substitute this value here and we get that x is equal to lambda y, but y is 8 lambda x. So we get that x is equal 16 lambda square x. We get that x minus 16 lambda square x is equal to 0. So we take a common factor x and we get that 1 minus 16 lambda square times x is equal 0. So then the solution of this equation is either 1 minus 16 lambda square is 0 or x is 0, right? So from this one, from x is 0, we substitute in here and we get that y is 0. But then when we substitute in the third one here, we will get that minus 8 is equal to 0, which is absurd. So that means that we don't get a solution in this. We continue then only this path that is going to tell that 16 lambda square is equal to 1, and then lambda square is 1 of 16, and then lambda is plus minus 1/4. Okay, so then we have two possible values of lambda. Let's start first with lambda equal 1/4. So if lambda is equal to 1/4, so we come back to our equation here for the value of x, and we get that x is equal to times 1/4 times y. So that means that x is equal y over 2. And then we substitute in the third of the equations and we get that for x squared, but x is y over 2 now, square plus y squared minus 8 equals 0. So doing the operations here, we get y squared over 4. So this is just y squared plus y squared equal 8. And so we have that 2y squared equal 8, y squared equal 4, and y equals plus minus 2. So then if y is equal to, then coming back to our equation here, we get that x equal 2 over 2, which is 1. And then we have the first of our candidates. The point will be then 1, 2. So that is the first one of our candidates. So if continue here, if y were equal minus 2, so then coming back to here, we get that x is equal minus 1. And we get then the next of the candidates, minus 1, minus 2. So that's all what we get for lambda equals 1/4. So now let's continue to see what happens when lambda is equal minus 4. If lambda is equal minus 1/4, so then x is equal minus y over 2, and the same that before, when we substitute now this, because the minus goes inside of the square, is not going to be any difference in the equation, right? So we're going to get again y equals plus minus 2. So we do again what happened when y is equal to, so we get that x is equal minus 1, and we get the next of the points, that will be minus 1, 2. And then when y is equal minus 2, so then we get that x is equal 1, and we get then the fourth point. So we have now these two other points to add to our list. So this completes the list of the candidates. Now the list of the candidates is going to be these 2 points and these 2 points. So what remains now is to actually evaluate the function, the original function, at each of the points in the list. F of xy, that was x times y, right? So evaluated at 1, 2, at the first of the points is our list, is going to be just 1 times 2. In this case, it's just 2. So f evaluated at -1 minus 2 is going to be also 2. F evaluated at -1, 2 is -2, and f evaluated at 1 minus 2 is -2. So we finish, then we complete the step of evaluating the function at all the points in our list. Then we have just to look at the values and decide which one is the smallest and which one is the biggest. So clearly the minimum value is going to be -2, right? And it's going to be reached at this point. So at -1, 2, and at 1 minus 2. There are 2 points in the domain, then that the function reaches its minimal value, that is -2. And from here we can see that the maximum value is going to be 2, and is going to be reached at 1, 2, and also at -1, -2. So these are the 2 points where we reach maximum value of this function restricted to this curve. We can extend the method of Lagrange if the function has actually more than one restriction. So for instance, if we have to calculate the maximum of a function f restricted to the conditions that the function g is 0 and another function h is also 0. So if we have a function with 2 constraints, so in that case, to apply the methods with 2 constraints, we have to write now this system of equations where we are going to write down each of the partial derivatives as introducing here the 2 Lagrange multipliers, and we're going to add then the 2 constraints equals to 0. So for example, let's calculate the extreme, the maximum and minimum of this function subject to now 2 constraints. So be sure that you see that this function has 3 variables, right? It's a function of 3 variables, which is going to be constrained to these 2 conditions. Let's first write the function g as a function, right, of x, y, and z. This is going to be putting everything in one side. It's going to be x squared plus y squared minus 1. And the function, the other one, h, is going to be h of x, y, z equals to x plus y plus z minus 1. Okay, so I remind you that the conditions are going to be that the gradient is going to be a multiple of the gradient of g plus another multiple of the gradient of the other function. And we are going to have to add the conditions g equals 0 and h equals 0. So in order to do that, first of all, we need to calculate all these gradients. This is going to be the first step. The derivative of f respect to x, so the function f is this, the derivative respect to x is going to be 2x. The derivative respect to y is 2y, and the derivative respect to z is 2z. Let's go now at the function g, and let's do the same. The derivative respect to x is going to be 2x, the derivative respect to y is 2y, and the derivative respect to z is 0. There is no variable z there. And then we do the same with the function h. The derivative of h respect to x is 1, the derivative respect to y is 1, and the derivative respect to z is 1 too. Okay, so now we put everything in the system of equations that we said before. Our system of equations is going to be, in this case, then the first equation will be 2x is lambda this mu plus mu this. So in this case will be 2x equals lambda 2x plus mu. The other one will be 2y equal lambda 2y plus mu. And the third one will be 2z equal mu. And then the two restrictions will be this equals 0 and this equals 0, which in this case are so this is the complicated system that we need to solve now. From the first equation, we get that 2x minus lambda 2x is equal to mu. And so then that means that 2 times 1 minus lambda x is mu. From the second equation, we get similarly the way that 2y 1 minus lambda is also mu. So this then is equal to this, right? Because both are equal to mu. So we get here that 2x 1 minus lambda is the same that 2y 1 minus lambda. We cancel here the 2's and putting everything in one side, we get that x minus y 1 minus lambda is equal to 0. And we have also from the third equation that 2z is equal mu. So we have also that z is going to be equal to x 1 minus lambda. From this equation, we get two solutions, right? Either x is equal to y or either lambda is equal to 1. So let's follow each of the two paths here. So first, if x is equal to y, then substituting in this equation, we get that x squared plus x squared minus 1 is equal 0. So then that means that 2x squared is equal 1. And that means that x is equal plus minus 1 divided square root of 2. So we have two possibilities here. So then when x is equal 1 divided square root of 2, so then we have that y, since x is equal y, right? Y is equal the same thing. And so we have then the values of x and y. For the value of z, we go to the last equation here, and we get that z is equal to 1 minus 2x. And so from here, we get that z is equal 1 minus 2 over square root of 2. So then we get that z is equal 1 minus square root of 2. And then we have the three components of the point. We have the first point in our list. So the point is going to be 1 over square root of 2. The y is going to be also 1 over square root of 2. And the z is 1 minus square root of 2. So this is then the first point in our list of candidates. We continue the method here. The other value was minus 1 divided square root of 2. Well, we do the same in this case. We get that y is the same thing, and in the same way we get that z is actually equal 1 plus square root of 2. And we get then the next of our candidate points. So the point is going to be then minus 1 divided square root of 2 minus 1 divided square root of 2 and 1 plus square root of 2. So then this is the second point in our list. So remember that here we explore this path, x equal y. So the next one will be lambda equal 1. So we continue here. What happens if lambda is equal 1? Well, then immediately if lambda is equal 1, remember that the value was coming from all these equations. So we see immediately that mu then is equal 0. And then if mu is equal 0, so we have automatically that z is equal 0. So we get the third component already. And then we go to this equation, so let's put z equals 0 there, and so we get that x plus y is equal to 1. And so then we have that y is 1 minus x. So if y is equal to 1 minus x, we go to this equation now, we substitute there x squared plus, instead of y, we are going to put now 1 minus x. 1 minus x squared is equal to 1. So we do the operations here, we get that x squared plus 1 minus 2x plus x squared is equal to 1. So we get that the 1's cancel, and we get x squared, 2x squared minus 2x equals 0. So that means 2x times x minus 1 equals 0. So two possibilities again here. We had either x is 0 or x is 1, right? 2x 0 or x minus 1 equals 0. Okay, so in the case x equals 0, we are going to get that y is then equals 1, because y is 1 minus x, substitute in there. And then that gives us the next of the point, right? The point will be then 0, 1, and 0, which was the value of z that we're investigating. So this is our next candidate. And from here, if x is equal 1, we substitute here, and we get that y is equal 0. And then still z is equal 0, so we get here the next of the points that is going to be 1, 0, 0. And so here is our list of candidates to be minimal or maximum. So as before, now what we need to do is to evaluate the function at these points. So let's evaluate. The last step then will be to evaluate the function at each of these points. So let's start. So if we evaluate f at 0, 1, 0, so remember the function is this one, we have to plug in the values of x, y, z, so we're going to have just 1 in this case. So if we evaluate the function as 1, 0, 0, we get also 1. So now if we evaluate the function at this point, 1 root of 2, 1 over root of 2, 1 minus root of 2. So we have to do the square of each one, right? That's what we need to do for this function. So the square of the first one will be just 1/2 plus 1/2 plus the square of this, that is 1 minus 2 square root of 2 plus 2. Well, we do the operations here, and we get that this is equal to 4 minus 2 square root of 2, which is approximately, because we need to know approximately to be able to compare, right? It's approximately 1.2. And then we do the same thing, evaluating at the last of the points here, that is minus this, and then minus this, and then 1 plus square root of 2. We do the same thing. We are going to get here again 1/2 positive plus 1/2 positive, and then we have here plus 1 plus 2 square root of 2 plus 2. And so this is going to be 4 plus 2 square root of 2. That is approximately 6.8. Okay, so now is where we need to look at all the values that we got, right? So will be the value 1, the value 1, the value 1.2, and the value 6.8. So we can decide now which one is the minimum and the maximum. So we get that the maximum value is then this one and happens at this point. And the minimal value is going to be 1 and happens at these 2 points. So we got then the maximum value of this function is 6.8 and happened at this point. And the minimal value of this function is 1 and happens at 2 points, 0, 1, 0 and 1, 0, 0.